Hello everyone, and nice to see all of you here today. So, Jacob community is on air, and we are happy that we finally continue our amazing series devoted to JDK 24 features. And based on your feedback and your recommendations, we decided to devote it to the performance deep dive. But as for the beginning, let me ask you to post your hello messages into a chat so we will make sure that everything is fine and you hear us and see us well enough. And until we're waiting, let me remind you that all the materials which you will see today, you will be able to reach on the Weir community platform after the event. The recording and yep. Thank you, guys. I see your messages. That's great. You can find the recording both on YouTube and Weir community platform. And as for the presentation and other materials, they will be attached to the talk page on the Weir community platform. Also, please do not hesitate to post your questions during the session in both Weir community and YouTube chat, which is more convenient for you. And we will try to answer all of them. And even in case if some of them won't be covered, we will definitely try to find some time to answer them after the event on the Weir community platform in the comments section. So none of the questions will stay unanswered. And I think that more or less that's it from the organization standpoint. Let me remind you that you can find our community on Weir community platform and join even more exciting events later. But as for now, let me share the micro with Yaugen. Yaugen, the floor is yours.
Okay, so hello everyone. Can you see my presentation, Tatiana? Tatiana?
Yep. Everything is fine.
Great. So, as it has been already mentioned, our today's topic is deep dive into some performance improvements and additions to GTK 24. I am your today's presenter. I have been a lead software engineer at EPAM Systems for quite some time. I have experience in multiple business domains. I'm practicing hands-on engineering and architecture skills. And from the tech stack standpoint, my focus is on Java, cloud, data, and NoSQL. And in spare time, I experiment with knowledge management and enjoy video games. As for ours today exact agenda, there are 5 major milestones. First of all, we will cover briefly what are the goals and non-goals of this presentation, because garbage collection and performance overall is quite a deep topic, and obviously we will not be able to provide a comprehensive guide here. We will be able to focus on some specific areas only. So it's nice to have some clear expectations from our talk. The next milestone will be about the overview of what Java offers in terms of garbage collection overall, because it will make it easier for us to discuss further results and some numbers, some technical details. Then I'll briefly mention what was the exact setup in terms of both hardware and software for the tests themselves. And finally, 2 major milestones will be dedicated, first of all, to some synthetic garbage collection tests to strengthen our understanding of how garbage collection works in practice. And finally, we will conclude with the most interesting part, which will be about benchmarking some LLM workload on Java machine. Without further ado, let's get into goals and non-goals to set some clear expectations. So about the goals. The goals of this presentation include to highlight different factors that might affect your choice of performance tuning and especially garbage collection for Java applications. Also, I'll mention some methodologies and tools that will help you to make those judgments as objectively as possible. As I've already mentioned, we'll overview some garbage collection foundation in terms of theoretical knowledge. And then we'll compare how JDK 24 compares to JDK 23 in terms of performance features. And as for non-goals, it's important to understand that we will not be able to cover everything here, so this will not be a step-by-step guide for tuning garbage collection in every situation. You'll have to do benchmarks for yourself for your specific production setup. Then we will not dive that deep into garbage collection implementation details because every algorithm is quite complicated, and we'll touch upon just the most important concepts to make it clear how we understand the test results. And finally, this will not be a perfect benchmark because perfect benchmarks take a lot of time to set up and conduct because you need a lot of data, a lot of iteration, etc., etc. And ideally, you need to cover different setups in terms of hardware and platforms, software platforms. So this will cover just some subscope of all that. And having that said, let's get a basic overview of garbage collection in Java. So first of all, about some choice factors for garbage collection. You must keep in mind what is your target platform. So this will be a big difference, for example, between cloud native or Internet of Things, where we have a lot of small underpowered devices. Then it's important to understand whether your non-functional requirements favor throughput versus per request latency, whether this will be long-running application, like, for example, some big ETL job, or this will be something very short and quick, like a serverless function. In terms of workload, you need to understand whether you will have some significant spikes in any of performance dimensions or not, whether you will load more of CPU workload or memory, or you will be I/O intensive. And finally, the data that you will process also matters a lot. So whether, and specifically in regards of garbage collection, it's important to know whether you will have a lot of small pieces of data or fewer but very large ones. As for the key garbage collection mechanics in Java, first of all, we have a generational hypothesis, which states that most of the objects allocated on the heap will be will become unneeded very quickly. So, for example, if we have some mathematical formula that performs multiple algebraic operators in a row, intermediate variables will hold data just for some moments and will be discarded, and what matters is the end result only. And this hypothesis helps a lot in terms of how heap is structured and how garbage collectors make assumptions about when and how to clean your objects. Then we have the biggest performance black hole for Java applications. This is stop the world pause, which happens when garbage collector is not able or is designed not to make any concurrent work with application threads and has to pause all of them in order to make its job. When it comes to structuring heap, first of all, we have so-called garbage collection routes. Those are objects which live for the duration of the whole application lifetime. So they are not removed until your application stops completely. These are things like thread locals, thread stack data, per class data structures loaded with the classes by the JVM, and some other special things. And it's key to garbage collection performance to be able to find those routes efficiently and track what they refer actually to. Then every garbage collection mechanism has its own per object structures, global data structures, and also leverages some special bytecode instructions to make its job easier. In terms of per object structures, garbage collectors often insert some headers to each Java object in order to store some small metadata like pointers, like usage stats, etc. As for global data structures, this is basically about how the whole heap is structured into generations, regions, or whatever the GC implementation chooses to do. And as for the specific instructions, these are typically so-called barriers. So basically, a garbage collector may choose to insert some sort of hooks like event listeners for every read or write operation in order to objectively understand how each object is used. And if we put it all together on the example of one of the garbage collection mechanisms available in JDK, namely Shenandoah, we can have the following picture. So this is a region-based garbage collector. It splits the whole heap into small regions. Every region may have a mixture of different objects, which may live for a long time or discarded quite quickly. Some of the regions on different phases may be freed completely or reallocated to adjacent regions. And basically, to make it work efficient, this garbage collector tries to make as much work concurrently with the application threads as possible and avoid stop the world pauses or any sort of pauses as much as possible, which makes it so-called low pause garbage collector. And it has different modes which help to fine-tune for specific targets like CPU usage, consistency of garbage collection pauses, or throughput. And if we take an example of load barriers, Shenandoah has the notion of load barriers, basically hooks which are inserted for reference access for every object. And this helps this algorithm to track which objects refer where and whether they must survive the next phase or not. And as for the use cases of this garbage collector, this includes applications with constant allocation rates, because this algorithm is not very efficient at varying rates when it's quite hard to predict how many objects you'll have next second. And also it's quite good at handling containerized workloads, which also do not tend to allocate too many new objects. And as for the pitfalls possible to happen with this algorithm, you need to keep in mind that there are some specific mechanics used by application code and libraries, namely weak references, which may affect its performance. And also you must pay attention to how many concurrent garbage collector threads are allocated for the algorithm to run, because in some situations, Java machine is not able to detect this number correctly. Some other implementations of garbage collectors available in JDK include ZGC, which is also a low-pose garbage collector, which is designed to scale for a vast range of heap sizes, ranging from hundreds of megabytes to terabytes, while maintaining pretty much the same overhead in terms of how much time it spends onto pauses. And as for the use cases, it's quite good at handling very big applications like those in big data ecosystem. Also, because of its scalability, it's able to maintain very low pauses for underpowered devices, like, for example, IoT. And also, it's quite good for applications which generate a lot of code on the fly, like those which support some sort of user scripting features. The other implementations include Juan, which is the de facto standard for many JDK generations. It's quite mature, but it has some higher overhead, which we will see in the test results. So in case your application is suffering from performance issues, probably it's worth to take a look at other implementations like Shenandoah, ZGC, or else. Parallel GC is basically the only use case for very small workloads which are extremely limited in terms of hardware available to them and application threads. Then we have Serial GC, which is the simplest implementation. It performs at the cost of having stop the world pauses every time it needs to do any work. So it has the lowest CPU overhead, but it definitely the worst one for throughput and even per request latency. Then we have some sort of experimental slash test garbage collection mechanism called Epsilon GC. It's basically an OOP garbage collector. So if you are absolutely sure that your workload will maintain a steady usage of RAM, you may use it and have no overhead at all. Finally, we have some non-standard implementations which are included into vendor-specific distributions of JDK, like SOC4, IBM, or SAP GC. And also we have some specifics. Actually, we don't have much of specifics of garbage collection in such platforms as AWS Lambda, GCP Functions, and other serverless serverless platforms. Sorry, at least at the time of this presentation. So there will be no difference whether you run on desktop or cloud or other platform. The choice of garbage collectors will be pretty much the same. As for the environment that was used for the testing, that was a pretty underpowered laptop with Windows 10, which is already outdated a little bit. Some quite decent amount of RAM, but not very good. I'd say that 32 gigabytes of RAM would be better, and an SSD disk. And for the tests, I've chosen to use G1, ZGC, and Shenandoah because G1 is the default garbage collector, so it's running by default all the time. And thus it's worth benchmarking, at least as of now. Then we have Shenandoah, which received a significant upgrade in JDK 24 in the form of a new mode, because previously it was generationless, and now it's able to leverage generations to smoothen some of its downsides. And finally, we have ZGC, which is the direct rival for Shenandoah because of how similar those two garbage collectors are internally, and because ZGC has already experienced a transformation from a generationless to generational garbage collector. So it will be interesting to see how maturity is compared to some novel experimentations introduced in Shenandoah. And finally, as for the GDK choice, I chose Liberica GTK 24 and 23 builds from Bellsoft because unfortunately Shenandoah is not included in the builds provided by Oracle, and also Liberica is completely free, both for non-LTS and LTS releases. Azul, for example, is not free for non-LTS releases, unfortunately. Now let's jump into the first part of tests. This will be about synthetic tests to see how our theory concepts map onto reality with different garbage collectors. And don't worry about this slide with some diagrams. It's just to show that I have provided some details on how every scenario was set up, what the code was doing, and all that information may be found on the link provided on the slide on GitHub. It's a public repository, so if you are interested, you may visit it later. But for now, just bear in mind that those details are available for your exploration if you're interested to do so. Then I have to pay some respect to the original article by Einat Balasin, which was done for JDK 13, and it gave me basically the structure and the framework for setting up my test sequence. Then the benchmarks were run with JDK 24, both with and without object headers compression, which is a feature that came out with JDK 24 exclusively. JDK 23 will run without it because of that. And I had one warm-up iteration of 10 seconds and 10 measurements of iterations of 10 seconds per test case. And all that thing was performed based on the GMH tool for performance testing. And now let's jump to some key takeaways that we can draw from the results. First of all, if we talk about object header compression, which promises to reduce heap usage in some cases quite drastically, and thus probably reduce the garbage collection overhead as well, because there will be fewer bytes to collect actually. But as for the synthetic tests, there was no significant difference, unfortunately. So probably this is because of the short-term nature of those tests, and some real-life applications might provide different results in this regard. And also, it's important to remember that object header compression is an experimental feature in JDK 24 and may receive boosts, for example, in JDK 25, which is coming this autumn and will be a long-term support release. Then, as for ZGC and G1, those both performed better than Shenandoah, which may be seen on this diagram. And that was exhibited for unpredictable allocation rates. But G1 is still worse than ZGC because it predictably an older algorithm and is not able to save that much of CPU time, unfortunately. The next takeaway is that in JDK 24, Shenandoah seemingly improved its handling of those actual varying loads. So to compare to the previous slide, you can see that the boost might be quite significant for both generationless and generational variants of this garbage collection mechanism. So probably this is due to the refactoring that has been done to this implementation in order to accommodate the new mode. Who knows? But overall, Shenandoah seems to prove its promise to deliver its promise on consuming less CPU. So it's better for applications that burn a lot of CPU in many threads constantly, which is shown on the bar chart below. Then in JDK 23, Shenandoah was significantly worse than ZGC and G1 as well in terms of raw memory allocation. So the case when we have just a batches of small objects allocated and immediately discarded. So in this situation, the amount of time spent per allocation operation was higher for Shenandoah. And in JDK 24, Shenandoah improved its score, but ZGC and G1 are still better in this respect. Then the next takeaway is about the situation when the application allocates a big portion, namely more than 30% of heap with some sort of maybe caches or pre-calculated data, and then starts to churn some new objects which are discarded more quickly. And in such situations, Shenandoah still performs worse because of having to allocate heavy objects and to analyze a larger leaf set. And to draw some conclusions from those numbers is that Shenandoah generational is predictably slower than its non-generational counterpart because it has to maintain more global data structures on the heap and sometimes perform more aggressive heap scratching in order to pick newly allocated objects more quickly. But it's still better than G1 in many cases, and even ZGC in some more specific cases. But unfortunately, it unexplainably demonstrates poor performance with a heap with a constant pre-allocation part. So in the test, I believe I used about 70% of pre-allocated heap. So probably this thing will be improved in JDK 25 plus, but let's see, because this new mod for Shenandoah is experimental and it's expected to have some issues. Next, the most interesting part, which will be about a more real-life-like scenario, and it will be about running an LLM, yes, inside JVM, thanks to JLlama framework, which allows to run some vectorized calculations on the CPU at the moment. Unfortunately, it doesn't support GPU calculations as of time of this presentation, but I believe they have a roadmap which includes integration with a so-called Tornado VM project, which allows to leverage GPU instructions in Java applications. And again, the module with this JLAM application is included in that same public repository on GitHub, which will be shared with you after this presentation. And in terms of business logic, this is quite a simple REST API application, which exposes an endpoint for taking a URL with a URL to some web article or wiki page, and it downloads the text content of it and feeds to an LLM to do some summarization. In terms of heap size, that was fixed at 4 gigabytes. It was JDK24 only to save some time on benchmarking. And in terms of parameter dimensions that were changed from test to test, that was garbage collector algorithm choice and object header compression on and off, sorry. And on top of that, I added some logging to see how much every garbage collector consumes memory for its global data structures on the heap, thanks to the native memory tracking option. And let's have a look at the table. Don't worry, I'll bring some more readable explanations on the next slides. It's just for reference. But overall, you can see that in terms of heap size usage, actual heap size usage, regardless of the fact that it was fixed at 4 gigabytes, G1 was the most efficient one. But as a downside, it performed the worst in terms of pause times and number of those pauses. As for the memory usage overhead, I'd say that most of the garbage collector algorithms consume pretty much the same amount of memory, except for ZGC, which consumed almost twice as much. And then we have the top performer in terms of CPU consumption, which is ZGC, but it also consumed the biggest amount of heap out of those 4 gigabytes available. Let's have a look at some pictures and draw some conclusions. So first of all, G1, as I've already mentioned, G1 was the most efficient in terms of heap usage, maximal heap usage, at the cost of more CPU usage in the form of pauses. As you can see on this slide, there are quite a few of them. Despite the testing iteration took just about 3 minutes. There were quite a lot of pauses, and they introduced some pretty significant spikes. But probably if we run the workload for more time, probably the picture would smoothen a bit. But unfortunately, I didn't have more time for this. The next takeaway is about ZGC. So as I've already mentioned on the slide with the raw numbers, ZGC provided the shortest pauses with no OHC. However, it did it at the cost of max heap usage, which tells us that probably the application failed if we tried to run multiple concurrent requests, because each test iteration was just one summarization request at a time. As for Shenandoah, it consumed a little bit fewer heap memory than CGC, and provided also much shorter pauses compared to G1, but it was somewhat worse than ZGC. Then as for generational Shenandoah variant, it wasn't much better, so pretty much the same picture, unfortunately. Shenandoah provided also very short pauses compared to G1, which is expected. Oh, sorry, that's a duplicate slide. Okay, so let's jump to object header compression. And in this area, G1 actually improved the picture. So as you might remember, just a few moments ago, we had a quite spiky picture, but on this slide, we can see that there are a lot of fewer spikes, and the heap usage is still quite reasonable and much smaller than for ZGC and Shenandoah. But on the other hand, object header compression somewhat made ZGC behave more unpredictable. So this feature definitely needs some improvements. Probably we will get some in JDK 25 plus. Let's see. And as for the memory overhead, which means the amount of memory allocated for garbage collection exclusive needs, Shenandoah and G1 provided the smallest overhead of around 130 megabytes. Shenandoah generational consumed a little bit more, which is explained by the need to track two different generations. And ZGC consumed most of native memory for its purposes. But if to believe to its design principles, this number should not change much for a lot larger heaps, even if it comes to terabytes of raw memory. And now let's have a look at a smaller but not less important feature in terms of performance improvement in JDK 24. If I'm not wrong, this project is called Laden, and it will be not just about this feature alone. It will be about overall how GVM, how to make GVM load and run faster, warm up faster, because Java applications are notoriously known for longer start times and the time required to achieve optimal performance based on such features as just-in-time compilation might be also quite extensive. So sometimes we choose other platforms like Python for serverless workloads. So the project Laden is dedicated to changing the situation. And the first effort in this area is about AOT class loading and linking, ahead of time class loading and linking. And the idea is that, just to remind you, the idea is that the Java machine is able to make so-called um, dry run to try to load all the classes, or at least all the major classes it needs to perform its business logic and other technical functionalities, and dump all the precompiled, preloaded data structures associated with those classes in a compact file, which is called AOT archive, so that subsequent runs of the same application are able to reuse it and get a boost in terms of startup times, at least. And the methodology was to start the LLM application in the recording mode, make one request and shut down. Then start LLM up to create the AOT archive. This is the second phase. And then, thanks to logging the difference between the moment when the control flow enters our main class and the startup time provided by the management factory bin, we can somewhat approximately measure how much it took to jump from the moment when the Java application itself started itself to the moment when all the major classes are loaded and we can perform some meaningful business logic. And as for the results, on average, with no AOT on the given configuration, the application took about 1300 of milliseconds to load its classes, its core classes. And with IoT, this number reduced almost twice, which is good. So the boost is around 43%, which is basically confirmed by other independent benchmarks on the internet. But still, it's not perfect. So, for example, such techniques as CRAC or GraalVM are still faster, albeit they are somewhat more complicated to introduce to applications, at least at this moment. And there are some pitfalls associated with the AOT class loading technique, because it heavily depends on the assumption that the environment in which you create the AOT archive is pretty much the same as the one you use in production. So this must be the same operation system. This must be the same CPU architecture. This must be the same JVM distribution. This must be the same JVM settings. And on top of that, you cannot use any instrumentation agents like those for hotcode swapping or even profiling, which is not that good. So probably these aspects will improve in the future. And overall, it's up to you to judge whether you are ready to spend more effort to modify your continuous integration and delivery pipeline to integrate AOT archive creation or not. But in any case, when the AOT archive is not usable by the current JVM, it's able to just start as usual, reloading all the classes from scratch as a fallback. So it will not fail. It will just start as usual, slower. And as for the information that I wanted to share with you, this is basically it. On this slide, you may find some useful articles, links to the materials that gave me inspiration to create those benchmarks. Also, you may find some details, some further details on how different garbage collector work internally, some case studies from real life, how, for example, LinkedIn and Netflix migrated to ZGC for many of their workloads. And finally, don't forget about the source code of all the tests, which may be found on GitHub repository. And probably this is all that I wanted to share. Now let's jump onto some questions, if there are any. Tatiana?
Thank you. Thank you, Evgeny. Thank you for the great and insightful presentation. I already see a lot of interest from the audience to your research and its results. So, guys, just a reminder of that. I've already shared the link to the repo in the chat, but it also will be shared together with the slides on the Weir Community Talk page, together with this recording. So don't hesitate to return back to this research later and test it yourself if you'd like to. And I see that there are some questions in the chat. So let's begin from the very beginning. So the question from a chat, Shenandoah is still an experimental GC. When we can expect it? I mean, in which upcoming release version?
If I'm not wrong, the generational mode for Shenandoah will be actually production ready in JDK 25. So till
Yep.
September.
Yep, I see that guys have already even shared the link to particular JEP 521, which is about this part. By the way, are there any, I don't know, known estimations about the non-generational part? So, or
Please
only the junior?
clarify what
So,
you.
generation less part, I think. Am I correct? The generational version will be released in the 25th JDK, and so its counterpart, generational one, I haven't seen the JEPs for that. Are
Well,
they
I
specific
believe
or will
sorry,
they
I believe
be
it's
part?
production ready already.
Looks
So
like I missed
the
something.
main
Yep.
point that I highlighted somewhere in the beginning of the presentation is that Shenandoah is just not included in most Oracle builds. So you
Yep.
have to
Yep.
use other GTKs to have it on
I
board.
see. I see. Thank you. Thank you for the clarification. So another question. If we are building a custom runtime image which focuses on reducing the deployment size of Java application for a mobile app, this avoids uh, mm, mm, building like the full GUI application. So does this action affects the choice of GC and whether it will affect the performance considering memory constraints of mobile platform, which they might have.
Well, for mobile platform, you will probably want to experiment with ZGC or Shenandoah because they bring smaller overhead in terms of CPU while not introducing any significant memory overhead. But for extremely small platforms like IoT devices, probably ZGC will be a little bit better because it's designed to scale from very small heaps towards incredibly large ones. And as a last resort, probably if you are chasing extreme performance goals, you might consider using serial GC, but it will bring some CPU overhead. So it's a question about the trade-off between using less memory and using less overall CPU power, but having far worse throughput. And also, if you are on the side of extreme optimizations, like, for example, replacing your object pools with pre-allocated arrays of objects. So I've seen those approaches in platforms, for example, which handle financial calculations, I believe. So in such situations, you may have understanding of how much memory you will use at maximum, and in this case, you might choose the epsilon GC, which does not do any garbage collection at all.
Yep,
Given the
but
assumption that your application will not run out of memory, of course.
yep. That's important. Thank you. So, uh, another, I think, mainly like remark, I would like to hear from you your thoughts about that. It seems all newer versions of Java heavily focused on the AUT and GCs. What do you think? Is this like the key focus for the latest versions from your observations?
Well, in terms of feature set or what?
Yep, yep. Which is the focus of let's say, features of new releases?
So do
Which
we compare focus on garbage collectors versus AOT or garbage
uh,
collectors and AOT versus other?
versus other features? Yep.
Well, I'd say that it's quite balanced actually, because if we look at syntactical improvements in JDK 24, for example, there are plenty of them. There are experimental APIs like Vector. There are um, quality of life improvements for quick experimentation in the form of the ability to run Java applications which are described just with one Java file, even without compilation. So there are stream gatherers, there are constant improvements to core APIs. So it's quite balanced, actually, I believe.
And there is one more related remark. It's worth to mention improvement in the vector API. They extended it in JDK 24. Java apps that do ML like Elastic etc. will certainly benefit from it when they adopted these new vector features. Is an open question. Absolutely right. We have even discussed these points during the first part of this series, let's say, of talks. So, guys, in case if you'd like to hear more about that, and in case if you haven't had a chance to visit us previous time, you can find the recording of the talk devoted to the, let's say, whole overview of GTK 24 features on the Weir community platform. So the Jacob community have posted the recording of it as well. And
Yes, and let me add a little bit on this topic. So regarding the vector API, it's not unstable. It's actually quite stable. Just the thing is that the developers haven't decided yet on the exact API they want to commit to. But in terms of stability, it's quite stable because JLama uses vector API as a mandatory feature. So it requires you to enable experimental features. And there are even applications like, for example, Brock, recently released, which is about AI LLM orchestration on Java. It also uses a little bit of local LLM inference with JLama, which uses Vector API. So it's time to experiment, I believe, already.
yep, totally agree. By the way, guys, while we are waiting for your questions, let me remind you that you have a great chance to say your thank you to the speaker using the Weir community platform capabilities. So please follow the link of the talk page and use the star buttons to rate the talk, rate the speaker, and the thank you button to share your appreciation words and your badges with our speaker in case if you like our event. And another question from a chat. How does GTK24 AUT class loading compare to Graal VM native image in terms of startup time reduction? Should we choose one of over the other? Or can we leverage from both somehow?
So, first of all, AOT is designed to run in the traditional setup of GVM. So when this is exactly the GVM, the true GVM, and Graal VM is not entirely equal to the usual GVMs like Oracle JDKs or Azul, etc. But in terms of performance, as I've already mentioned on this slide, such techniques as CRAC and Graal VM are notably faster than AOT at this moment. So if you are in pursuit of extreme performance optimization, you should look into native images. But if you seek just at some boost in startup times, you may try AOT. But it's important to note that AOT for now is just about startup time. It will not improve your overall application throughput when it's warmed up already. But Graal VM will probably be able to provide better performance in some cases.
Yep.
So
That's
those two things cannot be compared directly at this moment, unfortunately.
And yep, another part of the question was about whether they could be combined anyhow. Uh,
And I believe I answered this immediately. So the answer is
yep.
negative, I believe,
So
because GraalVM is a different virtual machine. It's not a traditional JVM runtime, and thus it even doesn't perform the usual class loading as per se.
yep. Yep. So just to emphasize that these approaches are quite different. By the way, it would be interesting how all of that stuff might be combined. As you've already mentioned, that there are some serverless solutions which have been provided by different cloud providers, which also are heavily affected by the cold start and all of that jazz as usually. And this might make sense possibly to consider for the cloud providers to adopt this new functionality somehow in their features AWS Snap Start or so in order to, I don't know, make them better somehow. Actually, I think that this is also about the different and possibly not so compatible technologies, but still. So the Snap Start is like the third part of this conversation, I'd say. So, how do you think would it be still, let's say, a competitor of these two, of the AOT and GraalVM native images?
Well, in terms of such features as Snapstart is already kind of snapshotting at the first run, at the training run, so it's more comparable to AOT. But to be honest, I don't know the numbers. We need another benchmark. And
Sounds
in
like a great topic for the next presentations.
Mhm.
Yeah.
And in terms of GraalVM, I believe I saw numbers that GraalVM is still more performant than Snapstart, if I'm not wrong.
Uh, yep. Actually, I remember that we had a talk devoted to that topic, and even several of communities across the Weir community platform had different ones. So, highly recommend to search for the platform. And I think our community was also the co-organizer of one of the talks where it's been discussed that at least some production use cases might. Work better with the GraalVM, definitely, rather than with usage of snap starts in terms of AWS Lambda.
But it's more
And
complicated to set up.
yep, and it still has some uh, let's say not disadvantages but trade-offs which should be taken into account. And one more question from a chat. Are there any performance differences in case of usage of ARM-based processors or different operational systems? So how do you think whether this affect such benchmarks significantly?
Yeah, well, there might be quite significant difference, I believe, because there are even separate JDK builds for different CPU architectures. And the benchmarks that we reviewed today were made on an traditional x86 architecture. So probably you may, if you have an IRM processor or you're able to run an IRM box somewhere in the cloud, you may take my benchmark and run it there and see how are the results.
Yep, and guys, by the way, in case if you do so, and in case if you have any additional thoughts after the talk, or in case if you're watching us as a recording and you would like to ask something, please don't hesitate to use Weir Community Talk page, and the comment section is exactly for you. You can post the questions there, and we will be happy to answer them additionally and share the expertise with you, as well as gain some expertise from you in case if you have your own results. So I think that mainly that's it about the questions from a chat. Again, one more time, many thanks for your great presentation. Guys, let me remind you that you can share your appreciation words using the We're Community platform talk page, rating the talk, rating the speaker, and using the thank you button. And in case if you watch us as a recording, you can do the same. So please don't hesitate to use this toolset as well. And finally, the reminder that the recording and all the links, all the slides will become available soon after the talk on the Weir community platform page. Please stay with us, with our community, Jacob, and follow us for more interesting events and topics. And in case if you're interested in continuation of the series, also please don't hesitate to post the comments about the new and interesting features of JDK 24 or possibly upcoming features of JDK 25 you would like to hear more about. So, thank you very much, colleagues, and have a good one. Bye.
Thank you very much. Bye.